Okay, so we just calculated these, right? We calculated that the curl of the gradient of a scalar function is always 0, right? And then we calculated the divergence of the curl of a vector field is always 0. Assuming at least that taking the appropriate derivatives makes sense and assuming Clairaut's in a little bit. But in nice cases, these things are 0. Which might cause us to think like, if the curl of some vector field is 0, and keep in mind this is a crap thought, like originally. But maybe, just maybe, like if the curl is 0, then f is the gradient of something. You guys see that? Like I know the other way. I know that if f is the gradient of something, then the curl of it's 0. And that causes me to wonder, like, hey, is that fundamental? Like, is it true both directions? In other words, if the curl's 0, is it automatically the gradient of something? The answer is most of the time. So the curl test says that we need f is, so if f is a smooth vector field, why am I assuming that things are smooth?
Does the same assumptions that we had for those theorems?
Yeah, in order to hit this with any of the fundamental theorems, I need this thing to be smooth at least on some kind of local area, right? Specifically here, what I need is for this thing to make sense, and this thing has Clairaut's in it, right? For the curl of the gradient of f to be 0, you kind of need the mixed partials to be equal, so you need Clairaut's to apply. So you sort of need to know that things are smooth enough so that you can play the Clairaut's game. You guys see that? So if f is a smooth vector field in R3, right? So we're playing three-dimensional games, so we could apply Stokes and stuff. And then we need a thing about the domain that I'm going to leave blank for a second, and the curl of f is 0. Then f is the gradient of some scalar function. You guys remember I gave you this a long time ago?
Kind of.
Are you smiling and nodding because I said that I gave this to you a long time ago?
Yeah, we had the theme where we kind of find the reverse of a gradient, and it's like try to find the original function, and we had g, like then plus g of x plus g of y, so we have to battle which one we found and see if they connect.
Yeah, so to actually go about this, right, you would do this like, okay, I'll take the anti-partials kind of and then see if I can balance that whole jazz. The curl test says if the curl is 0, then it might be a good idea to play that game, right? If the curl is not 0, you don't even need to try to play that game because it's not going to work. Right? You're not going to be able to produce a function for which this is the gradient. Okay, so this other thing is if the domain of f has the property that any loop, and by that I mean some little closed loop, can be contracted to a point in the domain.
So that just means to find it more, right?
No, it can be a little looser. No. So what I mean by this is it would be okay if there was a whole plane worth of problems, because you can't lasso a plane with a loop. But it would not be okay if there was a whole line worth of problems, because you can lasso a line with a loop. You guys see that? So like if your domain looked like all of R3 except for the chalkboard tray run out infinitely far in both directions, right? I can get a loop around the chalkboard tray by going in here and then around the back and then out the bottom and back, right? Or if, maybe better, if my whole problem was this infinitely long ruler, right? This is not clearly.
Yeah.
Let's make an assumption. So if that was my problem, I can clearly ensnare that thing by just going like this. Right? Like I'll just give it a hug and that'll cause a problem, because that loop can't be contracted to a point in that space. You see that? It's stuck around that thing. But if there's a plane, right, like if this wall is my problem, like a loop on this side, no problems. A loop on the other side, no problems. And you can't get around the thing. You guys see that? So that would also be kind of okay. That one would be a weird case. You'd have to deal with it in kind of a funky way. But basically the problem is lines are an issue, or at least things that run off to infinity in two directions are an issue. Points, like if there's a missing point, right, like here's your missing point. This loop doesn't look like it can be contracted, right? Except in 3 space, you can go like this.
Yeah.
Say.
Yeah.
You see that? If there was a line here, I can't run that same operation. It's cool with that? Even if I remove a whole disk. Like I say, okay, this whole disk is a problem. You guys see this? Like, you can't permanently lasso this thing. Like, you can try to cinch it up around the equator or something, but it'll just pop off, come over the top. You guys cool with that? Okay, so that's what I mean by this thing.
Oh, and 0 is missing its hat.
Oh, and 0 is missing its hat. Thank you.
I didn't get that.
Cool, cool. So what this says is, hey, if you want to find a gradient for a vector field, take the curl first. Check and see if it's 0. That's an easy test. Because this thing, right, where you're trying to balance those equations, is a major pain in the butt in R3. We haven't tried it because it's a pain. You can do it, it's similar, but it's a pain. If you take the curl and get not 0, you can just stop, because it ain't going to work. You guys with me on this? Okay, so let's think this other thing through. We're going to make a very similar test for the divergence. Okay, so what I'm thinking is maybe if the divergence of some vector field G is 0, then what?
There is a curl of that?
Yeah, then maybe it's the curl of something, right? Right? Like I'm just trying to classify when can you find an antiderivative, right? Okay, see that? So, maybe? I don't know. Turns out it's true, basically. We can do this thing called the divergence test, for which we just have to make similar assumptions. So, we need if G is a smooth vector field in R3, what do I need to play that game? Why do I need it to be smooth and kind of...
Okay, so
Yeah, basically the same as the other thing. I need to be able to take a curl of it, right? So I need it to be at least a little smooth. And then I need for some of the assumptions for Stokes and kind of divergence theorem objects to apply. So I want it to be smooth on some kind of like slightly bigger space. Okay. All right. Now I need to figure out analogies. What would be the analogy of curl of f is 0 here?
Divergence of G.
Yeah, like I'm maybe thinking, okay, so maybe divergence of G is 0. Did I forget a hat again?
Do not need a hat.
Nope.
Do not need a hat, divergence is a scalar function, right? So what I did was I checked, like, okay, maybe if the divergence of this vector field is 0, then maybe it's the curl of something, right? And I'm still going to have this other assumption about the domain to fill in, but the conclusion is going to be what?
Then G equals the curl of some function, right? Or some vector F.
Okay. So then G is the curl of some vector field F, right? In other words, you can find a anti-curl, right? You guys see that? Okay. My assumption about space. The other one was a thing about loops, right? Because I was kind of thinking about Stokes on that one. Right, because I had a curl. So I was thinking Stokes at this thing. On this one, what am I thinking? It's a divergence test, so don't stress your brain about which thing you're going to think about. Think about the divergence theorem, right? Okay, so this one's a little weird, because this one is if the domain of G has the property that any surface, really closed surface, right, bounds a region in the domain. Okay. What kind of thing is that going to have a problem with? Like, what do I mean? I mean, if you have in space, right, the domain of your vector field. Yeah. Any old surface that you make in there has to have an inside that's in the domain.
Points, lines, or planes would be bad, right?
Close. Points are definitely a frickin' problem, right? You guys see why? No?
Could you even say that a point was closed? It's just like.
So I'm talking about a closed surface, right? So I'm saying any closed surface.
Oh, lines and planes would be fine, right? Because you can't close around it.
Yeah, kind of. Hold it. Okay, so if this is our problem in space, right? Where's a surface that has, right? So I need to draw a closed surface that has that thing inside of it. How tough is that?
That's pretty easy.
Yep. There we go.
Sphere, right?
Yay.
Bam, inside has a problem. So missing points in my space are going to cause me a problem. Hang on. Sorry.
That's okay.
Line, right? Infinite missing line out of your domain. Like, that's not allowed. Can I get a surface around that? Like, can you make something out of bubble wrap or saran wrap that's going to go around that?
Not a closed surface.
Yeah, not close.
Well, you could make a torus.
Like a two-dimensional.
Yeah, so you can make a torus, right, that goes like this. But where's the inside of the torus?
Not there.
No.
It doesn't have that in it, right? It just goes around that thing. You guys see that? So points are a problem, but lines aren't. You guys see that? What about a plane? Like, is there any way I can lasso a plane with a bubble wrap?
No.
I don't know.
No. Right? Because if you try to, it's the same thing with this, right? If you try to lasso this with bubble wrap, you're going to have to, like, bubble wrap through it at some point. That's not a closed surface in the domain. Plane will have the same problem. You can't get the bubble wrap around it. You guys cool with that? Thank you.
Yeah.
Cool? So they are a little bit different, right? The problems are a little different. Because, right, in this case, I'm kind of thinking, right? I'm thinking, which theorem am I thinking with the curl test?
Divergence.
Yeah.
The curl test.
Curl.
Curl test, not.
There's a curl in Stokes'
Stokes.
theorem,
Stokes.
right? So
Sorry.
I'm thinking Stokes at this thing.
Sorry.
So I'm wondering, when can't I apply Stokes? Right? You can't apply Stokes when there's not a surface, right?
Mhm.
So if you make a loop that doesn't have a surface associated to it, then you can't apply Stokes, right? The surface that you would get is the surface from contracting that loop. Go for it.
So you can technically just question any function like normally would with any curl test?
So if you try to apply the curl test, right, what you're asking is this vector field that I've got on hand, right, this f, is it the gradient of something? Right? In other words, can I find an antiderivative? So the first thing I might do is say, okay, let me check. Is it smooth? Cool. You can proceed if it's smooth. Is the curl 0? If the curl 0, then you have good grounds to think that it's probably the gradient of something. But first you should consider, what about the domain? You guys see that? If the domain is adequately nice, in the sense that any loop can be contracted to a point while staying in the domain, then, yes, it's automatically the gradient of something. You can find that something by using the technique that we did before. Right? The divergence test says you can do a similar object, but the thing you have to check about the space is a little different. The thing you have to check about the space is that it doesn't contain any missing points. And so the domain can have missing lines or missing planes in it. You can't have any missing points. Whereas on this guy, you can have missing points, but not missing lines. And that's because of the theorem we're using to hit this. You guys cool with us? Questions still?